So our next topic is to talk about the shared nothing architecture that substantially all internet systems use today and what that means for scalability. And going back to our diagram, we started out at the top level asking about the connection between clients and servers. Now we're going to go one level deeper and look inside the server box to see what it's made up of. And as we'll see, there's three major building blocks that servers are generally composed of these days. There's the presentation tier or front end. That's a web server like Apache or Microsoft IIS. There's the application server. That's kind of where the action is. It's where your application code usually runs. We're going to be using one called Rack, which supports applications written in Ruby. And then there's a persistence layer or a storage layer or tier where data that's permanently associated with your application, like your customer data, would get stored, typically like a database. So in the old days, the web really began as a way for people to exchange static documents, graphics, and so forth. And early web servers had a pretty easy job. All they had to do was accept an incoming TCP request, figure out which file to serve, and get that file back into the browser. But very quickly, it became the case that the more interesting sites were actually more like running a program and having the program generate the page you saw. And if you think about it, this is the case for things like e-commerce sites where you visit a page, you search for some products, and what happens is a program has to get run to find all the products matching your search criteria and build a page on the fly just for you. So originally, people authored sites like this by saying, well, HTML is what the browser consumes, but what we'll do is we'll find a way to stick a little bit of code here and there into the HTML, and that code is what's going to create the content on the fly. And it very quickly became clear that the code was the interesting part. So the code became the tail that wagged the dog. It sort of moved out of the web server into its own home in the application tier. So now we're going to look at these different pieces and how they work and what are the implications for architecture of software as a service. So if the site is really about running a program rather than about serving a static file, well, when you're going to run a program, even if it's from the command line, you have to worry about things like how do you figure out which program to run? So which URI coming into the site, how do you map a URI into the right program or subprogram? How do you pass arguments to that program? How do you get the program to run on the server? What happens if there's an error? Who cleans up after the program and provides the error messages? So all of these tasks have to be handled in SaaS apps as well, except that instead of running programs from the command line or directly through a GUI, we're running them as the response to a request from a web browser. So because all of this kind of functionality has to be taken care of no matter what language you use and no matter what framework you use, frameworks have evolved to sort of support all of these common activities so that you don't have to. So really, today, it's more like you fill in the code that's specific to your application, and all of these other details like mapping URIs to which piece of code and how do you pass arguments from maybe stuff that the user typed in, how do you pass those to your code, all of those things are now taken care of by the framework. It saves a lot of work. Now, even within the logical architecture, where we said that there's these three different tiers, that's just a logical diagram. Another question is, how do those things map onto physical hardware? Now, in the case of the homeworks you're doing in this course, or when you're doing your own development of your own SaaS applications, typically you'll have a single machine that's hosting all of the pieces. So, this gray box here you can think of as your laptop, and on that same machine, you're running your own web browser to test things. You're running some kind of a presentation tier, and we're using WebRick, which is a really, really simple development web server that ships with Rails by default. It can only handle one user at a time, so not great for big sites, but it's fine when you're developing your own code. In purple, we have the application tier, which has an app server, Rack, that provides some of the machinery around allowing your Ruby code to run as part of a Rails SaaS app. We have the Rails library itself, which your code can use. And then finally, we have the storage tier where permanent data lives. Well, in development mode, the only permanent data is data right on your computer that you're using really for testing. So we're going to be using SQLite, which has a very good name. It's like a SQL relational database, which we'll talk about more in the next few segments. But it's so lightweight that only a single user at a time can use it. So this is kind of the baby version of the setup that's fine for one person developing and testing. When you move out into a production environment, typically you'll see something like this, where you really have multiple copies of the entire stack. You'll see that we've replaced WebRick with Thin, which is a production quality, very fast, very lean front-end presentation tier. We have many copies, so to speak, of the application stack that includes the presentation layer and our application code. And the reason we're able to do this, remember that we said previously HTTP is a stateless protocol. Every request is truly independent. Well, if it's really true that the only thing that ties together different requests from the same user is data that would be put into this persistence tier, then we should be able to create multiple copies of the app to serve many more users. We should be able to direct incoming traffic to any one of those copies because they're all independent requests and rely only on the stored data to tie together requests from different users. And this is, in fact, exactly what's done. Now, the reason it's a little bit more difficult, why I haven't drawn multiple copies of the database, and I'm using MySQL as a stand-in here, the database is a little more tricky because as soon as you have multiple copies of the database, that means there might be multiple copies of some data items. And now there's the problem of whether those copies can always be kept in sync if there's multiple databases. That is an open problem, and if you've heard about the NoSQL movement or of NoSQL databases, it is one of the problems they try to solve. And we're going to try to shed some light on what's difficult about solving that problem momentarily. In this course, we're going to be using Heroku for our deployment. They have a very similar environment, but they've custom engineered what they call dynos, which are sort of lightweight app servers that they can run. And each app also has databases devoted to it. It's got database caching built in so that commonly done database queries can be easily repeated. And they have their own technology for a bank of presentation tiers, HTTP servers, so that they can scale those out separately from the application servers. But the basic idea that we're coming back to is the same. The stateless parts of the stack, like the presentation tier and the app tier, can essentially be scaled out by making many copies of them. And with cloud computing, it's so cheap to have multiple machines that this is a very popular strategy. But sooner or later, the database is likely to become your bottleneck, and scaling that out is much more tricky, which we'll come back to in a moment. So what do people do when it's time to scale out the database? If you've heard the terms sharding and replication, one thing you might say is, well, if I have some data elements that are really not shared across different users, for example, my personal preferences, my user profile on a site like MyYahoo, well, one possibility is I could actually have multiple databases, and users whose usernames start with different letters might be stored in different databases. Now, that works really well as long as you never need to combine information from two of those databases, and then things can get pretty hairy. But this is called sharding, and the idea is that if you have some data that really never has to interact with other data from different users or from different entities in your application, you could just store that data on different databases. Replication is another solution. This says, well, why don't we have many copies of the database and only one copy accepts updates, because the idea is that updates happen less frequently than queries. And periodically, the updates will get propagated to the other copies. This is often called master-slave replication, and it's one way to do this. So what kind of data is it the case that reads occur much more frequently than writes? Well, think about Facebook and the idea of posting on a timeline or liking something. There's many more people who are going to consume the results of that than people who are updating it at any given time. So having some amount of inconsistency actually has been an issue for Facebook that they've done a lot of engineering to work around. It is the case that if you do an update to your timeline, there's a bounded amount of time during which not all of your friends will see it right away. They'll see it at slightly different times. Now, to their great credit, Facebook has done an enormous amount of engineering to minimize that window so that in practice, most people never even notice it. But the message here is there's no free lunch. If you try to scale your way out of the database problem by replicating, you're going to have the issue at some point where different copies of the data might not all be up to date. If you try to get out of it by sharding, you avoid that problem, but now you have the problem of data that's in different databases. It's really hard to combine and join together. So neither one of these is a solution to the database scaling problem, and it arises directly from the fact that in this three-tier architecture, scaling where the data is just hard to do. So to summarize the high points of the software as a service architecture, the browsers are the clients. They ask questions. They make requests to the servers. HTTP is the protocol that they use, and they use URIs and HTTP methods like get and post to name what they want to do. HTTP is a request-reply protocol, so everything begins with a client asking a question. Servers can't really push information to you proactively. They have to wait for the client to ask. Even in cases where it looks like the server is pushing information, it's really usually just the client asking over and over again. And in modern SaaS applications, when you make a request to a server, it's not going to serve you a static file. It's going to generate some content on the fly for you. HTML is the medium by which that content is encoded. CSS, or cascading style sheets, is how we control its visual appearance. And because HTTP was designed as a stateless protocol, cookies allow the servers to track different clients and to keep track of the same client coming back on multiple requests. So there's an important architectural trade-off that was made here, right? The architectural trade-off is stateless means you can actually scale out those middle tiers by replicating the app server or replicating the presentation tier in a way that you can't really do with a database. So in retrospect, you could argue that even though statelessness seems to introduce the complication of requiring cookies, on the whole, it was a good architectural choice because it allows parts of the application to be scaled much more easily. Frameworks like Rails and like Django and like others try to collect some of the common machinery necessary to support SaaS apps, like the machinery we've been talking about, and make it conveniently available to use so that not every new programmer has to reinvent the wheel. And finally, the mapping between these logical tiers and the shared nothing architecture, frameworks are responsible for giving you that too. They have to identify where different functionality goes, how the framework supports each piece, and that's what we'll explore in the next couple of segments.